So, my name is Florian, and I'm the co-founder and CEO of Trinckle. And I brought today my other co-founder Gunnar and CTO. We decided to split this presentation. I will give you a brief overview of Trinckle, and Gunnar will share some tech insights with you. So, let's start. We founded Trinckle with the mission to simplify design. And how we use computational design for it, and why we think it is especially beneficial in additive manufacturing, I'm going to show you now. To understand what problem, oh no, Teams? Ring. To understand what problem in additive manufacturing we're actually targeting, let's have a look at the very basics. What do we need to 3D print? We basically need two things. We need a 3D printer, and we need a design. The design contains the blueprint of the part so that the printer knows what to print. And here already the problem appears. Whereas most of the industry has focused on making these machines pretty good and unleashing a lot of great potential, we haven't seen big improvements in the design side, at least at the point that we still design very manual. Whereas in the world of physical goods, it was absolute normal, and it is still absolute normal, that we try to automate everything that is possible. But in the world of design, we're still somehow stuck to very manual process. That was and is okay in the world of mass production, where you have once very high design efforts, but can split or distribute them over thousands or millions of parts you actually produce. But in the world of additive manufacturing, there's much more complex parts and much smaller batch sizes, and in many cases even batch size 1 when it comes to customization. Here we cannot afford this high manual design costs, and we cannot afford this slow manual design processes, and worse, good designers are a very rare resource. And this problem actually hinders a lot of fantastic AM applications out there, and we thought, okay, how can we solve these problems? And there we identified 3 ways of how we can actually solve this problem. One is we make CAD systems just more powerful, so to increase the efficiency of the existing CAD engineers. Second, we make CAD software so easy that even non-engineers can use it. And third, we are able to automate design processes to a degree so that we do not even need any human interaction there. We at Trinckle focused at number 2 and 3. We therefore developed our own CAD system called Paramate, and with Paramate, we're able to quickly set up configurators for designing that are so easy that even a doctor could use it, for example, designing an implant or an orthosis, without the need of having studied CAD before. And with Paramate, we're also able to automate design processes fully. And this is especially beneficial when it comes to very repetitive work. For example, if you always have to design a robot gripping system according to the object it should hold. Put it into our system, and our system would automatically, for example, provide the arm, and our system would automatically construct the right gripper around it. Yeah, in what industries is our software mainly used? We mainly have customers in the automotive industry, more and more in aerospace, and nowadays also in medical. So, and if you now think, wow, that's interesting, I want to have a look at it, how can I use your software? Then we have 2 options basically. One is you define what you need, and we build such a custom application for you. We also now have a self-service option, so you can check it out yourself and work with the solution. And the other is that you use one of our so-called standard applications, where we gathered all the knowledge we have in one certain field into one application. For example, with FixtureMate. Here in FixtureMate, a non-expert can design all kinds of different fixtures without any experience in a few minutes. Yeah, how are we able to actually set up so quickly different kind of applications? This is mainly thanks to our Paramate system, which is here on the base. And Paramate contains all kind of relevant modules and functions that we need to build up these applications. And then it's pretty easy. We just, once we have a new product like a robot gripper, we just define the specs and definitions of such a robot gripper within the script. Our Paramate system then executes the script and gives out a configuration or an automation application. Then I provide the arm it should fit to, and then our system automatically generates the ready-to-print data. So and that's it from my side, and now I hand over to Gunnar.
Okay, I will take over about the technical part. Automation. Automation of design has the following aspect. So you can think of the amount of automation here on a scale between 0 and 100%. And if you look at the required knowledge or competence the user would have, actually you have kind of a reciprocal behavior. This means when you have no automation, you need to have really a CAD engineer to build your object. The higher you go within this automation, actually you come to a point where everybody can use the thing, and that's actually the goal. So when we're here at the 0%, we have classical CAD, so very trained people that actually can use it. Somewhere in the middle of the curve, this is what we call assisted CAD. This is also things that we are building where we have a certain scope, like the medical case, where people have to have some certain amount of knowledge, but not so much about the constructive parts, but still you have to somehow specify certain points or define certain aspects of the configuration of the construction. And then, of course, there is this end, and this is what we want to talk today about, what we call fully automation, where at the end you do not need to know anything. I mean, you have to know what you want to get, but nothing more, and get something out. So automation for engineering is half the way, and we can go the full way, and this is what we want to present today. We have this case. This is something that maybe you have seen this already. It's something that the Deutsche Bahn currently is installing on many stations. These are small signs mostly at handrails, but they can also be at some other places where we have directions or information written in kind of Latin language, Latin letters that everybody can read them, but then also in braille signs that also visually disabled people are able to read them by touching them with their fingers. This is an interesting aspect because this client really needs a lot of them, and they are very specific. You can think of that every station has different messages written on this, and you have a lot of stations in Germany, and this case actually now was a real use case where we printed at the end, or not we, but our client printed over 30,000 signs that were already installed. Insofar, this has a certain relevance. The system works I will show it in detail in a second, but in a brief overview, the system works in a way that the client, in this case the Deutsche Bahn, defines in a very easy way what signs they want to have. This actually goes into our Trinckle Paramate system. The signs are created in a very robust and functional workflow. They are then produced by a partner of the Deutsche Bahn. The company is called CFK, and then they are handed out, and they save a lot of money because compared to the previous way where they were designed sign by sign in the CAD program, this is now really a use case where you can run big batches of these things through it. How does it work for the user? So the user has an Excel sheet where he can define all of his text, all of his signs he wants to build. So I made here an example for a conference center. It would maybe look like this. He has the option to put additional bright text if he wants to have a different text for this sign. He He gives the radius of his handrail. Of course, this needs to be known because we have different sizes of this. And he can also give the width of the sign. And this is actually pretty easy, so every client can do this. You need no CAD expertise on this point. And then you go to the website of the that we prepared with. There actually on the back end, our CAD system, our Paramate system is working. Only thing you have to do, you have to upload the CSV file. You get an automatically you get the full set of signs as a preview. You can a little bit user interface stuff on top. You can actually highlight one, look at one. You also get the prices of this automatically calculated. And then you press on order. And then, of course, the magic starts in the background that actually all of the signs are automatically generated, placed into different stacks that can be then easily placed into the printing build space of the producer, and all of this is then transferred to the FTP server of the client. So when one wants to do this kind of fully automatization, you have to think of a couple of aspects that are more important here than in other fields. The first thing is, of course, you need to have simplicity. It needs to be that all the different decisions that need to be done during the production or the construction process need to be combined into your automatized solution. That the user using them doesn't have to know about these things at all. You need very guided processes. This means you take away the freedom of a CAD system where you can do everything and make it rather very railed, that you can do the stuff that you should be able to do and not more. And of course you need a high robustness, because you can always assume that the clients are putting wrong data, wrong stuff in there, and this thing has still to work, or at least give sufficient information back that the client sees, okay, here I did something wrong, I have to provide different data. All of this is covered in our approach, Florian was showing before, in our script-based CAD system, and ideally all of this is then embedded into one CAD process. This scheme shows it a bit, so CSV file in, and then inside the script you have the different steps. I simplified this a bit, but for today this is fine. So you have the translation of the clear text into bright text, you have the construction of the parts, you have to build the assembly for the 3D printing machine, and all of this then ends in a 3D model. Of course, these things are a bit more complicated internally, and what I said before, that we have to have this simplicity, that we have to somehow combine the complexity and put them into this model. And I want to give at least 3 examples for this case, how this technically works. The first thing is that, of course, you need to translate the clear text into bright text. Bright text is, maybe somebody of you have looked at this at one point, maybe not, is a kind of a language. It is, of course, every letter in Latin has some correspondence in bright text, but of course it's not always a one-to-one conversion. There are a lot of different rules, for example, recording numbers, special characters, and when you look at this, it is kind of complex, and the idea is that you can actually encapsulate all of these rules into the CAD system by itself. So you write the rules into the system, into the script, and then you don't have to care about this anymore. So you need no external solution, and then you can actually, then the system knows how to translate your clear text into the bright text. So it's kind of a certain covering of complexity. The next point that is interesting to show is the following aspect. So our client, who was then also producing the designs, had a requirement for the sintering process. He said, okay, our signs should not be longer than 29 centimeters, because then they would stick out of the build space. They should ideally not be much smaller than 12 centimeters, unless they are very small signs, but And inside this range, they should be as small as possible. And you would like to split long signs to reach these requirements. And of course, the splitting is also not so easy because the splitting needs to be done in a way that you only do the splitting in between character blocks of the Braille words and of the Latin text letters. And then, of course, ideally in a very centralized way, though the split line here is in the middle and should be evenly spaced on both sides. And yeah, I mean, that was the requirement, and we said, okay, we will do this. And it's, at the end, it's a logical problem that is not so hard to grasp. It's a little bit like a text editor is doing this as well. But still, it needs some thought, because, I mean, you can have the situation where you say, okay, none of these blocks are actually fitting, so I have to somehow add some spaces in between to make these things fitting, that I really can get these cutting lines, and the logics, not super complicated, but it's still a little bit of logic that you have to apply. So you have to walk through this flow chart, for example, where you have to compare the lengths of the Braille signs in every position and the length of the letters in every position. Then you have to calculate which is higher than the minimum, which then is smaller, where you put the different extra spaces and so on. So I don't want to go into this in detail, but it shows a little bit that you need to have a certain amount of logics or complexity that you want to put into your CAD construction as well. And especially interesting to see is you cannot really put this outside. One could, of course, think, okay, if I have a classic CAD, I make another program which calculates these things, and then I put the results into the CAD. But this does not work that well, because you're also accessing elements from the construction itself. So this red box, for example, is one step where you take the width of your already constructed letters and analyze this. And of course, this then is somehow dependent from each other. So you don't have a simply forward construction where you have input, construction, and output, but it can depend on the intermediate process. We have other examples where this happens in a more complex way than here, but I mean, in this Braille sign example that I wanted to show, this is here some point where this takes place. So this is something that can be introduced then in our system, in our script. And then we come to the third aspect where we show that this kind of logical integration into one CAD construction script is very interesting. And this is for the build space preparation. So our client said, okay, I do not want to get all the STLs of all the different signs separately, and then I have to place them manually in my build space. I rather want to have that you give us already batches of signs that are already aligned with a certain angle, that are actually ordered in the way that the package is as close as possible. This means that we have to order them by handrail radius. So we have the one with a higher radius on the left and the one with a smaller radius on the right, that they can be stacked more properly. And then they also should be aligned with a spacer support structure at the bottom, that all of this could go directly into the printer. And that we could do. So we added this also into this CAD construction, and all of together this really became a very nice use case. So the things could be printed then here. This is how it looks like for the printer. And all of this goes into the script. All of this can be then combined in one module. And I think this is an important aspect that we wanted to show today, where we say, okay, by doing this, one can get such a system very easy to use. And at the end, it's a fire and forget system for the client. And with that, he was then able to produce this larger amount of signs. So that's the end. Thank you very much for listening. Thank you. Florian, our team. Are there questions? Or